All right, let's start. Yeah. Today I will go over a little bit of like the ancient cryptography and then cryptography basics. And then yesterday I released the 4 challenges, and then like there will be more challenges coming through as the contents of the lecture goes by. But could you please stop talking? Yeah. All right. So and then like at the end of the lecture today, I will give a little bit of tutorials about like how you can solve and then submit the flag. And so like you can get onto the server environment and then get familiar to how to submit your answers and get score. Right, and then like the lecture slides are like right now available. So like if you want to download that, please visit our course website, cs370 at unexploitable.systems. And let's start. So cryptography. So it looks some of the esoteric, and then it feels like the hard thing to learn, but because this is just an introductory class, I don't want to get into the like a super detail about the cryptography, but we will just cover the nutshell of it and then know how to use it securely, conceptually. So the cryptography is used when you need to communicate with the others securely and also for privately. And then we will learn about like some other properties of the cryptography, but right now we will focus on the confidentiality of the data here. So suppose you want to tell someone else about like where do you want to have dinner today? So I would like to have a dinner at Local Boys. So like suppose you want to send this kind of message. But the problem is that like if I just speak out like this, so even if I just want to tell that to Benjamin, but all the other students can know that, yeah, Youngjun is going to go to the Local Boys, and then like they hit there and then like ask Youngjun for 5 food. Yeah, so that could be possible. Yeah, so although you guys are thinking that like our internet is secure or something, so the internet is designed without any kind of security at all. Yeah, it's quite surprising. And then the security engineers, yeah, they developed a lot of security technology and then borrowing lots of things from the cryptography to implement secure and private internet is available. Yeah. So when you are sending packets over TCP or UDP on the internet, it'll be actually similar to like you speak out the thing to public. Yeah. So cryptography can make our communication secure. So conceptually, it's something like you have the plain text message, and then we can lock it with the lockbox and then give out the key to the other end. Then only the other person who got the key can open it and take a look at the plain text. So conceptually, this is something like that, but how we are implementing that is something like we will scramble this kind of the plain text message. Looks like totally random number to the attackers. So in that case, even if we would like to say this kind of the plain text, it will be scrambled like this. And then what the attackers are observing is, what's that random number? Yeah. And then the other end must know what the plain text is. That's why without doing that, like we cannot communicate each other. So the other end must know the plain text. That's the requirement of the secure communication. So we need to find some of the way that we can scramble our plain text data like this, and then send it over to the other end, and then guarantee that only the other end can decrypt it, but all the other entities don't know about it. Yeah. And then this kind of the cryptography has been used in an ancient era. So I'm not sure if there's the other history about like recorded in the history about like using the cryptography. There is. So like there was someone like who used some of the wood stick and then write some of the so having a little bit of paper and then just lower over it and then write down in a vertical direction and then just expand it. then like all the letters will be like the scrambled, but the only one who has the circular dimension of the wood stick can decrypt it. That was the more historical one. And then like the sum of the documented scheme is so-called the Caesar cipher used in the Roman Empire, and like around before the Common Era. Yeah. And then the Caesar cipher algorithm is very simple. It is so-called substitution cipher. The reason is like it substitutes each character with some other character. Yeah. So the algorithm is very simple because at that era there's no computer. So like it must be human computable. So what they did is like they just shift the alphabet characters by 3. Yeah. So they definitely use some of the Roman alphabet. I'm not sure that alphabet is identical to the alphabet that we are using, but conceptually, it's something like if we have alphabets from A to Z, then just shift 3. So A, B, C, then start with D. Then we can create this kind of table. Then suppose you have a message, hello. Then how we can encrypt that is like the H is K, E is H, L is OR, and O is R. So we can encrypt the message hello as a KHOOR. Yeah, I'm not sure that's in the English dictionary, but yeah, some of the looking like a alphabet word, but yeah, don't know the meaning. So then, suppose you would like to send the message encrypted with the Caesar cipher. Then the plaintext message is hello, but the ciphertext would be KHOOR. So the attacker don't know what it is, while the other end, who know the exact algorithm, can easily decrypt by subtracting 3 and then offsetting 3 backward to change the KHOOR to hello. So is it secure? Yeah. Now everybody knows that the substitution by 3. Yeah, that's easy, right? So attackers may have this kind of table, and then they can also compute that. Yeah. So it's not completely secure, and then like it's a fake security. Yeah. I'm not sure, but that's why Caesar was assassinated. I'm not sure. Yeah. But unfortunately, they didn't have like a secure scheme for that. Yeah. So the Caesar cipher was too easy. So there's some other folks like try to advance on top of it. So these pictures are I searched it from Amazon, so that you can actually purchase these kind of things. I'm not advertising it at all. Yeah. So some of the more advanced cipher than the Caesar cipher is a rotation-based substitution cipher. And then what that means is that so previously the offset was 3. Yeah. Then what if we can choose the offset at the time of the communication or something? Yeah. So the outer circle and inner circle, we can rotate that. So they're not just for the offset 3. So if that offset is 19, then like it is A will be matched with T, B will be matched with U, something like that. So we can choose any kind of offset between 0 to 25 because the alphabet length is 26. So that is so-called rot n cipher. So rotating with offset n. Yeah. And for this kind of cipher, we can set whatever n between 0 and 25. Yeah. And then the premise is that like if you don't know what the n is, then you cannot decrypt it. That's not true, but yeah, let's assume that suppose that's true. Yeah. So the example will be changed like this. So anyone who knows the offset can decrypt the ciphertext. So we can share the shift value to the other end. And then say hello. And with that table, it will be URYYB. Yeah. And then if the attacker takes it, and if the attacker only knows about the Caesar cipher, then they cannot decrypt it. Is it secure? Not at all. Yeah. And then now we are living in the era of the computers. So even without the computers, you can easily decrypt it. But what you can do is try to shift every single N and then try to find some of the valid word in here. Yeah, there's a KHOOR, but you will eventually find hello is here. Yeah. So this is easy. So this is one of the example that you guys need to do when solving the challenges that I prepared for it. Yeah. So the implication here is that this kind of the substitution cipher is not secure at all. Once you know the internal algorithm, so algorithm itself is the key, right? Then you can easily decrypt it. But even if you don't know the rotating number, you can try it for many times. Then you can know the plain text. Maybe you can increase number of the N for this increasing the search space. Yeah, that could be one of the possible way to make it more secure for the RTN cipher kind of thing. But to do that, you need to have a very long alphabet. Yeah, to not being able to compute with the computers. Then the question is that, what is a secure cryptography? So from the ancient history, we always learn from the history, and then those crypto schemes are very weak, yeah, and we can easily break down. So one guy, whose name is Klaus Shannon, yeah, is so-called the father of information theory and modern cryptography, because he built a lot of the principles and theories and like the information theory and cryptography. So he defined a perfectly secure cryptography scheme. And his intuition is that, so from the figure that I show you first, something like this. So if there's a plain text message, but if we can scramble it and look like a random number to the attackers, then they cannot guess it. So Shannon's intuition is very similar to that. So if the attackers cannot distinguish a message, so not the message of the like the ciphertext of the message M from a random number that we randomly draw from like a random number generator, then it's perfectly secure. So the intuition is that like the attackers will observe one of the ciphertexts. Then if the attacker cannot tell if this is a random number or encrypted message, then we are secure. That's the thing. And then there is a more formal definition. Yeah, I don't want to go over this kind of stuff, but this is an educational class, so we need to go over this. But I will explain it step by step. So suppose there's a set of message. So you can think it of like any kind of valid sentence in English. Yeah, that could be the set of the entire message. Yeah, but that kind of message would have a distribution D. So the distribution here is that the probabilistic distribution. Yeah. So that not all sequence of the alphabets are not valid English, right? So that there's some of the grammar and then some of the words, and then we need to fit into like all that kind of the syntactical stuff. Yeah. And also semantically, the sentence need to be valid to be a plain text. And then if we just choose like randomly choose any kind of the sequence of the alphabet, that would be hardly to be a valid English. So what that means is that like the distribution is not random at all, but for a valid message in English or any other language, so for any other information that has certain syntax and semantics, they do have this probabilistic distribution is totally apart from a random. Yeah. And then that kind of distribution is known to the adversary. So suppose I want to send a message to my supervisor, the department head, Tom Weller, yeah, in English. Then you guys at an adversary, yeah, I'm sorry that pointing you guys as an adversary, but just making an example. Yeah, want to know that what Youngjin tells to the department head. Then you will know that I will use English, right? So that means that the distribution is easily to be known to the adversary. Yeah. And then from the example of the internet is something like that I broadcast to everybody, right? So if I send an email message to Tom, then that will be broadcasted to the everybody. So if you capture the packet on the Wi-Fi of the OSU secure or something, yeah, you can easily get all the packet. Yeah. And then from that packet, you guys can observe ciphertext, the encrypted message of my message. Yeah. And then how Shannon defines the perfect secrecy is that there is the knowledge of the adversary. So before observing the ciphertext C, so the adversary's knowledge is that just knowing the distribution of the English. Yeah. And then after observing the ciphertext C, so this notation is like the conditional probability. So after observing ciphertext C, you know also the distribution of the English. Yeah, that's the knowledge of the adversary. So this Shannon's definition of the secrecy is that, so when the attacker know only about the distribution of the English, and when attacker also observe the ciphertext and know about the distribution of the English, and then those two distributions are exactly the same. What that means is that the ciphertext does not give additional information to the attackers. If that is true, then the crypto scheme is perfectly secure. So it's okay to not to follow all the steps of the probability or like the distribution, those kind of thing. But the important implication is that perfectly secret scheme does not give any additional information to the attackers, no matter how many ciphertext the attacker observes. So the fact is that like when I send the message encrypted, then you guys can always see that kind of the ciphertext. But if I use the perfectly secure scheme, then no matter how many ciphertexts you observe, you will have no knowledge gain at all. That's the perfect scheme. And then that's the Shannon's definition. But the modern cryptographers redefine what's the meaning of the perfect secrecy. And then, so that is, so suppose we have a key generation algorithm here, and then two messages from set of M, which is like suppose we have a two valid message in English. Yeah. And then we will try to encrypt message 1 and message 2. And then with the sum of the key, there is a probability that the encrypted message will be the fixed ciphertext C. And then there is also probability some other message to be mapped with the same ciphertext. And then those two probability need to be same. And then I'm also sure that some of you cannot follow what's the meaning of this kind of the equation. Yeah. But because this class does not set the pure math probability as a prerequisite, I will explain some of the implications. So the implication is that we will encrypt with some of the scheme, and then the scheme is perfectly secure if we encrypt any two of the messages, and then there's a chance that depending on the key choice, there's a chance that this message mapped with a fixed number C, and then there is a chance that another number will be mapped with the fixed number C. Yeah. So those probabilities is exactly the same. What that means is that the attackers don't know which message it is among the entire English space, even if they see the ciphertext. Yeah. So the important thing is that making the knowledge gain would be 0, no matter how many messages the attackers are observing. So you might feel that this kind of stuff is quite abstract. So I will give you a concrete example about that. So a very simple XOR, the exclusive OR based cipher, is perfectly secure. Yeah. So it is with the perfect secrecy. So you might be surprising because like the XOR encryption is something like whenever we have a plain text message, we apply XOR per each byte. So what that means is that, so the scheme is that like suppose there's a message, we will prepare the same length with the message as a key, but draw that key from the random number. Yeah. And then how we calculate the ciphertext is that, suppose the message is HELLO, hello. And then the ASCII code, which the computer will process the English string alphabet, so that they will use a byte code for the so-called ASCII, and then like the H will be mapped into the hexadecimal number 48, E will be 45, L will be 44C or something like that. And then we can prepare a key, but I told you that the key must be selected randomly. But to give a good example, an easy example, I just set the key as a B, C, D, E. Yeah. And then its ASCII code is like a 41, 42, 43, 44, 45. Yeah. So that you can easily assume that in the ASCII code, the capital A starts with the 0x41 and then ends with the 5 something for the Z. And then like the lowercase a starts with the 61 and then end with the 7C as a Z or something. Yeah. So it's monotonically increasing by one. And then the XOR encryption, what it does is like it apply the XOR operation between these two numbers. Is there anyone who don't know what is the XOR operation? This is good. Yeah. So XOR returns 1 if the 2 bits are different. And then if 2 bits are the same, 0, 0 or 1, 1, then it will result in 0. Yeah. So like after applying the XOR operation, so we will get the ciphertext as a 97F8A. Yeah. That's the ciphertext. And then how we can decrypt the XOR cipher is that because if we apply the XOR with the same number again, then it will actually reverting the effect of the applying the XOR. So what we can do is the ciphertext is 0x9, and then what we can do against this ciphertext is that if we know the key, so first byte of the key is 41, so we just apply the XOR again to the ciphertext with the key. Then we can get HELLO. Yeah, something like this. And then in Python, you can change some of the bytecode to character with the function chr. And then you can also change this kind of the character string into the byte sequence using the function ORD. Yeah. I believe the ORD comes from the order or ordinal. Yeah, I'm not sure about that, but the function name is like that. Yeah. And then to give this as an example in bits, so I extracted this from the Wikipedia. So they use the example string wiki. So it's a bit format is something like this. So I just show the example as a hexadecimal numbers for the shortened form, but actually it works like the bitwise operations. So 0, 1, then 1, 1, 1 will be 0, something like this. And then like because of the XOR operation, if we apply the same key to the encrypted text, then we can get the plain text again. Yeah. So this is how it works. One question.
Is it pretty safe encryption, or is it like, or is there like easy ways to decipher without cipher?
So it's very simple, like the way, but I will describe why it is perfectly secure. Yeah. So to make it as a perfectly secure, the important thing is that we need to choose the key randomly. Yeah. The reason why is that, so we know that the distribution of the message is not random at all, because we will get the message from the set of the English or set of the Korean if I use my mother tongue, right? So that distribution is not completely random at all. But what we are doing is that, so if we draw the key completely random, and then with the XOR operation, yeah, it will make the distribution of the ciphertext completely random. Yeah. So that's the thing. So no matter how you choose message M in any kind of the message set, if you apply XOR with the random key that you draw from random, then the distribution of the message will be completely random. Yeah. So previously I used a very silly example of like using the ABCDE as the key. It does not look like random, but if you draw the key from the random number, then it'll be completely random. But you guys might be worrying about like there's some of the way to defeat this kind of the cipher scheme. So one of the caveat is that if we reuse the key, then we screwed up. So the important thing is that like the length of the key must be the same or more than the length of the message if we want to keep it perfectly secure for this kind of the XOR-based cipher. So what that means is that, so suppose I reuse the key for sending several messages, but you guys might know that every first message that I'm sending include hello something, yeah, or hi something. So it's so-called known plain text attack. So think about like the chatting message or like the email message. I mostly use hello right, at the first of the message. And if you know that, then you can recover the first five bytes of the key by just XORing that with the ciphertext. So for example, in the previous example, the ciphertext was 97F8A, okay? But if you know that that message corresponds to hello, then just XOR the byte sequence of HELLO, and you can recover the key. Yeah. So the thing is, we should not reuse the key. So for every hello message that I'm sending, I need to draw the new key. Yeah. So it's practically hard to use because think about it. If I just want to encrypt it for my own purpose, then I can virtually generate the super long key and then store it in my disk drive, and then that's it. Yeah. But the purpose of like using cryptography could be sending a message to the other guy. In that case, the other guy must know the older key. That means we need to pre-share the key length for the message that we would like to deliver over the network. Yeah. So that makes like this kind of the XOR cipher practically impractical for like using as the perfectly secure. But this kind of, because this scheme is perfectly secret, in addition to the key exchange algorithm, we will learn that later. Yeah. After sharing some of the good key and then generating a random byte sequence, and then we can use this kind of the XOR cipher because it is a perfectly secure scheme and it does not harm the underlying cryptography. So we will learn about like how this kind of the XOR cipher can be used in reality in a secure way in the coming lectures. But today I would like to emphasize that the XOR cipher, even if it does look like very simple, if we draw the key from the random distribution, then we can make the entire message, their encrypted message, their distribution is a completely random. Yeah, so it's perfectly secure. So the generic version of the XOR cipher is so-called one-time pad. So we don't have to apply XOR. We can just add or subtract or some other like the inversible arithmetic operation over the entire plain text to mix that with the random number. Then it will be, its distribution of the ciphertext will be like a completely random. Yeah. And then if you visit this Wikipedia website about the one-time pad, what it says is that so the resulting ciphertext will be impossible to decrypt or break. What that means is like it is perfectly secure. Yeah. If the key size must be as long as the size of the plain text. So if we have a 100 byte of the plain text, then we need to have at least 100 byte of the key. And then key must be random. So we need to choose the key randomly. And then the random here is not about rolling the dice. So for example, suppose you roll 2 dice, then you will get more results 7 than any other numbers, because the combination of the two will result in like the 6 cases for 7, 5 cases for the 5 and 8 or something like that. And that's why in casino, the craps game, yeah, you will lose everything when you get the number 7. Yeah. So yeah. And then that's not the uniformly random. So the random here means that like in the cryptography scheme, we need to use the securely generated random. Yeah. And then what that means is like mostly like we need to get a random number from the uniform distribution, not the normal distributions like that. Yeah. And then number 3, key must never reused in whole or any part. And then that example, the counter example of that one was like if I send a lot of hello message and then using the same key, you can recover the part of the key like that by doing the operations with the HELLO. And then the fourth one is like the inherently true. We need to keep this key secretly. Otherwise, like anyone who knows the key can decrypt the cipher, right? So this is the description about the XOR cipher, and then example of the perfect secrecy. Any questions for the contents for today? Yeah. So the lecture part ends here, but I will show how you can get onto the server and then solve the challenges. So yeah, if you already solved the challenges and then have no questions, you are okay to leave the classroom. But if you want to learn more and then try to take a look at how the challenge solving goes, then please stay in the room. Yeah. Then please give me a time for preparing about the tutorial. Can you guys see the text on the screen? Yeah, is it to be better to be bigger or? Yeah. Right. Yeah. So like I prepared some of the script to like get the challenges set up in your home directory. So whenever you get onto the machine and then under your whatever directory, so what you can do is running fetch crypto, then it will create the subdirectory as crypto, and then you can get all the challenges like this. Yeah. And then whenever there's a new challenge, then you can create this kind of thing again and again, and then it will fetch the newer things to the subdirectory. And then we have our scoring system. And when you get onto the CTF that unexploitable systems, you can see the matching challenges. So that we had 4 challenges are available, and then each challenge is about the solving the Caesar ciphers. Yeah, I can see there are already like 11 solves. And then like I posted that like at 10:48 or something, like if someone started right away. So somebody like they solved all the things before midnight. Yeah, that's good. Yeah. And then there's a ROTN challenge and ROT multi-round, and then like the XOR crypto stuff. Yeah. Then you can also read about the descriptions here, and then working on the corresponding challenges on the terminal. So let's start with the Caesar cipher. So we just learned about the Caesar cipher, and then that was like the adding 3 as an offset, and then having the substitution on the plain text. And then let's get onto the terminal. Then there's a Caesar directory. And then your goal is to read this flag file, but I set it up. You cannot read it without solving the challenge using this minor program. And then how I can do that is that, I don't know, is that this flag file only has a owner and group permission as a read. So the owner is root. You don't have to root permission. You cannot read it. Also, your group ID. So then my group ID is currently something like this. And then your group ID does not allow reading this flag. So that without owner in the group, there's no permission at all. You cannot read it. But the program, the Caesar, this program has a user and group as a week 1 level 0 solved. And then this is just a group name. And then what does mean at the second pair of the permission, R-S. So this S means that while running this program, it will inherit the group ID of this program, which is this group. So this program Caesar, when you are running the program, that program can read the flag. Yeah. And then that's why you can get the flag throughout running this program. And then in the most of cases, it will ask some of the question. And then if you answer it correctly, then it will give you out the flag. And then I'll show you how you can solve it. So I'm using Tmux to solve it with the interactive Python, and then I will demonstrate like how you can solve it with the interactive Python, and also like the coding into like some of the code and script, code in script, and then solve it automatically. So the first thing is I just run the Caesar program, and then this is the text I got. Yeah, and then I'll run my Python, and then this is a string that I got. But since the program does not substitute some of the dots or something, the apostrophe, something like that, it only substitutes the alphabet word. So what I will do is set this as one of the string and choose is there a function like that? No, right? There's no lower. Do you know how to change the lowercase to be like a string? No. All right. Too lower. Let's search for it. Oh, that lower, right? Yeah. Then like it gets the some of the characters, only the characters, and then I can map it. So let's just making all the lowercase, and then so we have this kind of array, and then what we will do is then we will also transform this and by the like shifting -3, and then what we will do is get the byte value of that, and then subtract a, because like we want to make the a as 0. It's the byte, and then -3, but the a would result in the negative result. So I will plus 26, and then get the remainder of 26. Then it will roll back, and then always return the positive number. And then I want to change it as a character, but the character number should add the byte of the a. And then I'll join the string. So it seems like somewhat valid English string. So that I'm just demonstrating some of the silly and then handy way for solving it. The first one is the capital character. So I'm typing like that. Something like this. Then you can get the flag. Yeah. There's a one way to solve it, but I do not recommend following this direction. Yeah. The way that I recommend is so that I put the template of pi. This is a script that you can use to interact with the program. So let's copy template.py as a solution.py. And then let's take a look at what it is. So what it does is like it internally uses so-called pawn tools, which I use for the library that I use for like the hacking some of the binary programs, but we will not use it intensively. We will use that to interact with the program. And then what it can do is like it can run the program, and then we can get the string output through the console as a programmatically, and also we can supply the console input to the program in programmatic way. So if I run the program, it speed out one line and then give us a ciphertext as terminated by new line, and then another line for the meaningless give me the plain text. So what it does is it just read the line of some of the first message, and then the second message is the ciphertext. So we read that from the program and then strip it to remove the new line coming in, and then it will print the ciphertext. And then it will receive the give me the plain text, the third string. And then next we need to supply the plain text of the ciphertext. So what I will do is I will just put the quit function at here. Yeah. So what it will do is like it will receive the first, second, and third line, and then regarding the second line as a ciphertext. Then let's take a look at the result. So it print out the first line and then receive this text as a ciphertext correctly, so that you can verify that whether the script received the console output correctly, because I intentionally print out the ciphertext with the prefix ciphertext and then print out the actual ciphertext, right? So we can verify that the ciphertext variable stores the console output ciphertext correctly. And then let's just skip the decrypt function for now. And then what it will do is that in the script, we will call the decrypt function. So you need to implement the decrypt function to solve the Xor cipher. And then if you supply the ciphertext, then you can get the plain text. So it will decrypt the plain text, and then it will send the plain text result to the program. And then right now, what this decrypt function does is for each character in ciphertext, so for the characters in lowercase and then the uppercase, then whatever, it just don't decrypt anything. So just adding the character C, to the same character to the plain text. C is a variable for each character of the ciphertext here. So right now what it does is it sends back the same ciphertext. So the program says wrong answer. And then what you need to do is implement decryption of the Xor cipher here. So let's do the same thing. So we can get the byte number of the character. And then, because in this range, all the things are lowercase, by subtracting the byte number of the lowercase a, we can get 0 for A, 1 for B, something like that. And then we want to offset -3, but having a negative offset could result in the negative result. So we add 26 because the entire alphabet size is at 26, and then get the remainder of it. Then we can operate it in a circular fashion. And then we add the byte number of the small case a, then we can create the character like this. So I actually put the example of this kind of the formula at here, so that you can change the capital A or the variable here to get it correctly. And then because it will be the same for this one, but just change it for the uppercase. And that's it. So now our decryption function decrypts the Xor cipher by having a negative offset by 3. And then let's try to run it. So here's a ciphertext, and then it decrypted it correctly, and then you got the flag. Let's run it again. So for the longer ciphertext, it decrypted it correctly. So the recommended way for solving the challenges are the coding in a Python script. So I know that you guys are not familiar with the pawn tools. That's why I'm supplying the template script. So we will mostly using the interacting with the binary program by send line or receive line, those kind of things. And then our design challenge is easy for that kind of parsing. So they don't worry about that part. So just regarding the using of the pawn tool is just for the bridge to the the interacting with the program. So any questions for having this kind of approach to solving the challenge? No? That's good. Then that's the thing. And then next is about solving ROTN. So the ROTN challenge is that like the not just for 3, it will randomly choose the rotating offset, yeah, among the 1 to 26 and 1 to 25. I removed 0 because like it will just show up the plain text, yeah. So if we run it, then the composition is the same, but right now this is not about the Xor cipher. So I will just try to copy Xor cipher solution to here and then run it. I need to change the binary name as a rod n. Then offset 3 does not match with the current challenge. Then same thing for the another ciphertext. Maybe there is a chance that the offset 3 may match, so you can rerun every time, several times, then you can eventually get the solution. Yeah, but don't wait until that. Yeah, I know that you guys are smarter than that to solve the challenge. So there's a template. Let's copy the template of pi as a solution of pi. And then it has a very similar structure. So it runs the raw n and then strip it, then get the ciphertext, then print the ciphertext, and then get give me your plain text string here. And then it also has a decrypt function. And then at the end, it will decrypt the ciphertext and then send it back. So you need to decrypt this ciphertext. But how I prepared this decrypt function is that because we don't know the number n for the rotation. So it will run over all 26 offsets. And then for the ciphertext, you can decrypt for every single choice of the offset. And then at the end, for all 26, it will show up which one do you want to choose. And then from your input, it will return the plain text. So as you have seen in this slide about like how the attacker can decrypt hello, yeah. So index 13 was a hello, right? Yeah. So we are actually doing the same thing with the program. And then, so let's do the same thing. So I just want to copy this one here. And then in this case, the offset is not 3. The offset is defined as a variable I here. So I just replace that to I. And then for the lowercase part, we'll change it like this. So I finished the writing up the code for that. Run it. Then can you see the correct plain text among these 26 choices? Is it here, right? Yeah. If you type 23, then you can get the flag. Then run it again. So it will change the thing. But from J, it could be either I or A. So you can easily find I don't have something like that. Yeah. So please use your domain knowledge for like getting like the string quickly. Yeah. I also felt like it's hard to get the right word correctly. So it is something like here. Yeah, that's the thing. There is a question from Zoom about the due date. Yeah, the due date is October 10th. Yeah. So you can do that. And then I will not demonstrate the challenge for the tutorial for the challenge for the RTN multi-round. And then what it does is like it runs the RTN for 10 rounds. So I intentionally designed this challenge to get all of you get familiar to the using of the Pun tool and Python, because like if you do decryption this by hand or interactive script, yeah, you'll get a lot of headache. So please don't do that. Please be smart and using Python script to automatically solve all these round of the thing, and then like they get the flag. I have seen that one of the students leave the message and then, oh, I failed on round 8. I need to do it again and again. Yeah. So yeah, you can do that, but there's a more smarter way to solve that. So please use the Python script about that. Yeah. And then next is about the XOR. Yeah. So it also has the template.py. So like it gets all the meaningless lines, and then we get the plain text, the ciphertext, and then like the require the text for you. Yeah. And then I just want to describe like how you can solve this challenge and then what this challenge means. So we have learned that the Xor encryption is a perfect secrecy, but the caveat is that like we shouldn't reuse the key. Yeah. So this is the case of like the Xor encryption, reusing the key, so you can break it. So what it says is like, so the key is 40 bytes, and then it will send the encrypted string. Yeah. So what it says is like, this is a plain text, and then this is the ciphertext of the plain text. So this is the same case that like if you know that I'm sending hello every time for the first message. So it's something like that, you know what is the plain text message of this ciphertext. But the XOR encryption, yeah, if you apply the XOR again, or if you apply XOR between the plain text and the ciphertext, you can get the key. And then, so this kind of format, so each of the 2 digits are corresponding to 1 byte data of the bytes. And then like this is just a hexadecimal number. So 01 is like the number 1 as a byte. And then 5F is what is that? The 95 in hexadecimal number and decimal number, right? Yeah. So that will be corresponding to like that kind of number. Yeah. So the entire length of this hex string is 80, but how you can convert this into some other type of data is that, so this is a hex string. Length of the string is 80, but there's a command that you can use a decode hex, then it will decode into the sum of the byte stream. And then length of this byte stream is exactly 40. And then you can get what is that? You can get the integer byte values by getting like the ORD of each characters from that byte stream. And then after that, what you can do is apply XOR for each byte between the plain text and the ciphertext, then you can get the key. And then, so it shows the plain text and the ciphertext, and then by XORing between these 2, you can get the key. And then after getting the key, you can decrypt the secrets. And then it expects the answering the plain text of this as hexadecimal digits. So you can do the byte by byte XOR and then make it as a byte stream and then convert that into hexadecimal numbers and then submit to that. And after that, the program will read this flag and then flag will be encrypted with that key and then sent back to you. So the final step of the thing is like you need to decrypt the encrypted flag with the key that you recovered. That's the challenge of the XOR. It's perfect challenge. Any questions about this challenge? So the challenge will gradually require you to have more program on it, but the program is just a manipulating string bytes in Python. So yeah, it might be easy, but if you have questions during solving the challenge, please leave the questions on Discord. Yeah, and then I will post our TA office hour online over Discord, so you can also send a direct message to our TA during that time. Any other questions? Yes. So I will post this recording at the end of the lecture. Yeah, and then YouTube requires a little bit of like the processing time, so it will be available after 6 p.m. ish. Yeah, I'll do it right away. Yeah. And yeah. So all the things will be posted on the lecture, the course homepage. On the left. Course homepage. Yeah, so you can get to the schedule, then there's a calendar format, and then like that, I will have a video link for each lecture. Yeah. So this is the end of today's material, and then I will stay here up to like 3:55. So like you can work on the challenges here and then ask any questions to me. Yeah.